Today, we'll be talking about the greedy algorithm. It's not a specific algorithm per se, but it's a problem-solving heuristic of making the locally optimal choice at each stage. It's easier to understand with an example, so let's forget about the greedy algorithm and look at the following problem. Let's say you live in Canada. I chose Canada because that was where I was born, and in Canada, the coin system is as follows. You have a toonie, which is a coin that represents $2, a loonie, which is $1, a quarter, which is 25 cents, a dime, which is 10 cents, and a penny, which is 1 cent. These are the 5 coins that we have, and let's say I want to make change for $3.49. But I want to minimize the number of coins I use. What would be your strategy? As a very experienced cashier, since I worked at McDonald's for 2 years, what I would do is I would try to use the coin of the highest value first, which is the $2. In this case, I can only use one of them, since after subtracting $2 from my total, I get $1.49, which is less than $2. Next, I will go on to the coin of the next highest value, which is $1. I can only use one, and once I subtract that from the total, I get 49 cents. I do that again with the coin of the next highest value, which is 25 cents. I subtract that, I get 24 cents left. Next highest coin is the dime, which is 10 cents. This time, I can use 2 of them for 20 cents. So I use 2 10-cent coins, and now I have 4 cents left. With 4 cents left, I can only represent them using 4 individual pennies, each worth a cent. So the coins I have now is 1 $2 coin, 1 $1 coin, 1 25-cent coin, 2 10-cent coin, and 4 1-cent coins. So we get a total of 9 coins. And that is actually the best solution, which minimizes the number of coins to represent that total. This strategy I did was called the greedy algorithm. So let's look at our definition of a greedy algorithm again and deconstruct it. Basically, what this is saying is that your algorithm will compute your solution one step at a time, and each step will make a decision that is locally optimum. And lastly, it will not backtrack and change that decision. If we look at our strategy with the coins, what we did was at each stage, when we have change left, we would choose which coin to pick. We didn't really think ahead. We just looked at the amount left at the moment and based our decision on that state without considering what we've picked and what we're going to pick in the future. Hence, that is what we mean by we compute our solution one step at a time. Then, our solution was to just take the highest value coin that you can get as long as it does not exceed the amount left. So if there was $1.49 left, we would just pick the $1 coin. Hence, this is what we mean by local optimum, which means at this stage right now, the best way to minimize the number of coins is just by picking the highest coin value without thinking about what happened previously and what's going to happen ahead, hence a local optimum. So then, once we've made that decision, we never look back and change the configurations of our coin. We just continue forward, choosing our coins and reducing the amount we need to make change for. You will see that this might cause our final solution to not be the optimal solution in some cases. Now, the greedy algorithm worked well in our Canadian coin systems, and it will work every time if we use that system. However, this strategy will not work in general. What if our coin system was 20 cents, 15 cents, and 1 cent, and I want to make change for 30 cents? Then the greedy approach will yield 1 20-cent coin and 10 1-cent coins, which gives us a total of 11 coins. However, the best solution would be to use 2 15-cent coins. So despite us choosing the 20-cent coin in the beginning, it's clearly a local optimum, but definitely not the right choice for the overall problem. However, because it's a greedy algorithm, like we said, it will not backtrack and change that decision. Thus, we now also learn that the greedy algorithm does not necessarily produce the optimum solution. So the difficulty comes in identifying if a problem can or cannot be solved with a greedy algorithm. So how can we come up with a strategy that works no matter what the coin system is? We will talk about that in the next lesson, which is about dynamic programming. I'll see you then.